Welcome to Chapter 16, Properties of Curves. We're going to talk a little bit more about taking second derivatives and what that physically means to a function. Part A, tangents and normals. If you can recall from the investigation, tangents and normals are lines that we draw along the function. Tangents are related to the derivative because the gradient of a tangent is the derivative. Okay, so you can't really take the slope or the gradient of a curved function because it doesn't have a straight side for you to measure rise over run. But you can draw a tangent, which is a line which goes along the function and touches the function at one and only one point. And if you draw that tangent, then you could take the gradient of that tangent. And if you do that, it happens to be the same as the derivative of the function. Now the normal is actually a perpendicular to the tangent. So it actually crosses the function at kind of a 90-degree angle if the function were straight. Now before we start into this, let's recall the point-slope form, which is the way to write the equation for a line. Let's write the point-slope form for a function with a slope of 2 or gradient of 2 and one coordinate defined, which would be 1, 3. What does the equation for this line look like? It looks like this: y minus 3 equals 2 times x minus 1. Okay? So the x1 and the y1, you substitute in the coordinates 1, 3. There's a negative in between the coordinate and the x and y variables. And the slope 2 goes right there. Okay? If you manipulate the function so that you divide both sides by x minus 1, you'll see that you get y minus 3 divided by x minus 1 equals the slope 2. And you can see that the slope, which is 2, is actually equal to the difference in y's over the difference in x's, which is the equation for the slope. The only difference is, instead of having 2 known points, one of the points is unknown. And the unknown point can take on any xy pair that's actually on the line. Okay, so if you still need help with that, come on in after school, because equations of lines is one thing that Maths SL assumes that you know well and does not review. So use the point-slope line equation from above to write down the equation of the tangent line at point A of y equals f of x at right. Use the point A, which is a comma f of a, for the known point, and use the derivative of f of x at point A, written as f dashed of a for m, the slope. So we're going to do the same thing that we just did, except now instead of numbers we got a bunch of variables. So we'll have y minus the y coordinate, which is f of a, equals to the slope, which is f dashed of a, times x minus a. At what angle is the normal line relative to the tangent line? It's at a 90-degree angle. It's perpendicular, remember? The blue line is perpendicular to this red line, and that's how you define the normal. Write the gradient of the normal to the curve at x equals a in terms of f dash a. So the slope, or the gradient of the red line, is the derivative of the function f at point A. Now remember that, or maybe you don't remember, but let me tell you again, the perpendicular to a slope of, let's say, 2 would be the negative inverse. So like the perpendicular of that slope, or the gradient, would be negative 1 over 2. So the perpendicular, or the normal, of f dashed of a would be negative 1 over f dashed of a. Okay, so that's what we're going to put here. We're going to put negative 1 over f dashed a. Now it asks us to find the equation of the tangent to these three functions here, and it tells us to do that at specific points. And in the first two cases, they give us only the x-coordinate, and in the last case, they give us the x-coordinate and the y-coordinate. Normally, when they ask us to find the derivative at a certain point, the x-coordinate is all we need, but in this case, it's nice to have the y-coordinate. It saves a little bit of work, and we'll see why. Okay, so let's do a first. So we have a polynomial or a quadratic here, x minus 2x squared plus 3. Remember that we're going to use the equation y minus y1, which is a known y-coordinate, equals the slope times x minus x1. The slope here, let's see, we're going to find, let's see, y dashed. It's going to give us 1 minus 2 times 2x, and the derivative of 3 is 0. So that is 1 minus 4x. And then we want to find what is the derivative when x equals 2. When x equals 2, the derivative happens to be 1 minus 4 times 2, which is 1 minus 8, which is negative 7. So we know that the slope is negative 7 in this case. We also know that the x-coordinate is 2. The only thing we don't know is the y-coordinate. How can we figure out the y-coordinate? Oh, look, there's this equation here, which gives us the y-coordinate given the x-coordinate. So we have y equals 2 minus 2 times 2 squared plus 3, which is equal to 2 minus 4 plus 3, which is 5 minus 4 equals 1. So now I think we have all the information we need. We just write in the equation. It's going to be y minus 1 equals negative 7 times x minus 2. And that's it. Now we do the same thing here for this one. The derivative of the function is 3x squared minus 5. If we evaluate that at x equals 1, it's going to give us the slope that we're going to use for the tangent line. It's going to be 3 times 1 squared minus 5, which is equal to negative 2. And then we do need to know the value for y at x equals 1. We just plug it directly into the function. Y equals x cubed, which is 1. 1 cubed is 1. Minus 5 times 1, which is negative 5. And that will be negative 4. So we'll have y minus a minus 4, which is y plus 4, equals negative 2 times x minus 1. Okay? Last one. Let's see. Let's find the derivative of this one. Y dashed is equal to, and let me rewrite this using the some exponent tricks here. So this could be written as 3x to the negative 1 minus x to the negative 2, remember? So now we can take the power rule, not so hard, and we get that minus, we're going to 2x to the negative 3, right? Because the negative 2 comes out front, multiplies by times that subtraction sign. So, and let's evaluate that at x equals negative 1. So we'll have negative 3 over negative 1 squared, which is just 1, so negative 3. And then we have plus 2x, 2 over x cubed, which is negative 1, so it would be negative 2. So actually it would be negative 3 minus 2, which is negative 5. And now we already have the x and the y coordinate. They gave it to us, so we don't even need to do this part. We don't need to do this part where we evaluate y with the function. We already know that y is negative 4. So we just put in the m value there from the derivative, and then we put x minus a negative 1, which is x plus 1. So that was actually easier because they gave us the negative 4 y value there. So now take a look at example 2 on page 387, and then we're going to do number 2a here. Find the equation of the normal to, and they give us a simple parabola here. Remember that the normal is simply the perpendicular to the tangent at this point. So we just need to find the derivative. Now let me just draw a picture of this, show you what it looks like. So there's, since it's an easy one to graph here. Y equals x squared looks like that, right? And 3, 9, let's say it's right there. And let's say you're going to draw the tangent. The tangent would look like that, right? Follows along the function. The normal, on the other hand, is a 90-degree angle to the pink line. So it would look kind of like that. And it happens to go through this point, 3, 9, because that's where we defined it to be. And it's going to have slope, which is -1 over the slope of the tangent. So it would be -1 over the gradient of the function at this point. So let's find the gradient of the function. It's 2x, right? Let's evaluate it at x equals 3. And that would be 2 times 3, which is 6. So now we already know the m is 6. And I think we can write it out now because we already have the point it goes through, which is 3, 9. So we have y minus 9 equals the slope, 6, times x minus 3. Okay? What about this one? I'm not going to try to graph that. That's a big mess, isn't it? Let me try to rewrite it using negative powers. X to the -1/2 minus x to the +1/2. And let me take the derivative of it. And then I'm going to find out what m is going to be in that linear equation. So let's see, -5/2 times x to the -3/2 minus 1/2 x to the -1/2. Okay, that's the derivative. And then we're going to evaluate the derivative at x equals 1. So first we have -5/2 times 1, which is -5/2, minus 1/2 times 1 to the -1/2, which is also 1. So we have -6/2, which is -3. So, and we already have the x and y coordinate of the point. How nice of them. Y minus 4 equals -3 times x minus 1. The only mistake that is easy to make here is that, remember that if you have two positive numbers for the x, y coordinates, that the negative signs actually are included in the standard equation, so they're negative there. Okay, maybe this is the last two. Find the equation of the horizontal tangents to, and what do I mean by horizontal tangent? A horizontal tangent would be a tangent that, like, let's see, if we have like a parabola like that, the horizontal tangent, the only horizontal tangent would be this one here, right? The tangent that goes through the vertex would be a horizontal tangent. So basically what we're looking for are tangents with a gradient of 0. So let's first find what the gradient in general for this function is. We just take the derivative, 6x squared plus, and then we have 6x, and then we have minus 12. And the derivative of 1 is 0. So that's the derivative. And then we want to know when this is equal to 0, because that's when you have horizontal tangents. So when is the derivative function equal to 0? This is, hey, remember chapter 1, quadratics? Okay, we factor out a 6, and then we are going to find the solution to see when this is equal to 0. We can factor it. Let's see, how about x plus 2, x minus 1? Does that work? It does. So the solutions to this are x equals -2 or x equals 1. And so we could, there are two tangents, maybe. And so let's try the first one. Let's see, what does y equal when x equals negative 2. What point would that be? So we'll put negative 2 in here, here, and here, and we'll see what we get. So that would be 2 times negative 2 cubed, which would be 2 times 2 times 2, it would be negative 8, plus 3 times negative 2, which would be a negative, let's see, a negative 2 squared, which would be 4, positive 4, times 3, which would be 12. And then we have a minus 12x, minus 12 times negative 2, which would be positive 24, and then plus 1. So that would be negative 16 plus 37, right? Looks like 37 here. So 37 minus 16 equals 21. So let's see, the y-coordinate that corresponds to negative 2 would be 21. That was a lot of work, wasn't it? I think 1 is going to be a lot less work. So let's see the y-coordinate that corresponds to x equals 1. It would be 2 times 1, which is 2, plus 3 times 1, which is 3. 2 plus 3 is 5, and then minus 12, negative 7, plus 1, negative 6. Okay, that was a lot easier. Okay, so those are the 2 points, and we know that the gradient, the gradient of the horizontal tangent is 0. So now the equation y minus x1 equals m times blah, blah, blah becomes much simpler because there is no m. M is 0, right? So we just basically have y equals 21 and y equals negative 6. Those are the 2 equations for the horizontal tangent. Okay? C. Find k if the tangent to y equals 2x cubed plus kx squared minus 3 at the point where x equals 2 has gradient 4. Okay, so let's see. So basically we need to do the same thing. We need to find the gradient function, or the derivative, which is 6x squared plus 2kx minus 3, derivative of minus 3 is 0. And we need to figure out what value is k such that when x equals 2, the gradient is 4. So we could just put in 2 for x here and here, and then we'll set it equal to 4. Okay? So we'll have 6 times 4, which is 24, plus 2k2, which is 4k. When does that equal to 4? Well, k is, I guess, equal to negative 5, right? I mean, we could do the algebra. 4k equals negative 20. K is equal to negative 5. Okay? So, that's it. That was easier than I thought it would be. Okay. Consider the curve y equals x squared plus ax plus b, where a and b are constants. The tangent to this this curve at the point where x equals 1 is 2x plus y equals 6. Find the values of a and b. First of all, the equation they gave us for this line is kind of unfriendly. It doesn't give us the gradient just looking at it because it's in standard form. Standard form is kind of useless for graphing and for pulling out information. So we're going to put it into slope-intercept form or gradient-intercept form. Basically, if you put y on the left and everything else on the right, that's gradient-intercept form. So we're going to have y equals negative 2x plus 6. If you remember, in gradient-intercept form, the number that's multiplied times x is the gradient. So the gradient of the tangent is negative 2 at x equals 1. So we know that the derivative at x equals 1 is negative 2. So let's find the derivative of this. Are you noticing a pattern here? We're always finding the derivative of the function. Okay, when in doubt, take the derivative. So that is equal to the gradient negative 2. Let me erase that. That is equal to the gradient negative 2 when x equals 1. So if I put 1 in there for x, 2 times 1 plus a, that is equal to negative 2. Because at x equals 1, the gradient is negative 2. Okay, we just ignore the y-intercept. We don't really need that yet. Okay, so 2 equals, let's see, a is equal to negative 4. So we already have a value for negative 4. Now we need to find a value for b. Now I think it is important to look at the y-intercept, and we're going to see about that. So the function we now know is at y equals x squared plus, or negative 4x minus 4x plus b. And we know that one of the coordinate pairs at x equals 1, let's see, what is the coordinate pair? Y equals 2 times 1 plus 6. So when x equals 1, y equals negative 2 plus 6, which is positive 4. So the point, which is like, let's say we got a quadratic here, and we have a tangent line. We have a tangent line that goes through a point there on the parabola. So you can imagine here, okay, this point here happens to be x equals 1, right? One of the coordinates is x equals 1, and the y coordinate we just found out by putting it into this line equation that it's 4. So it's 1 comma 4 is the point, okay? And so since we know that the point here, 1 comma 4, is on the parabola, we can also put 1 and 4 into the parabola equation, and that should give us b. 4 equals x squared is just equal to 1 squared, 1 minus 4 plus b. So that would be negative 3, 7 equals b, right? So b is equal to 7. So the two values are a equals negative 4 and b equals 7.